Hello everyone, we are Team Peanut Prince from Chinese Taiwan Catholic Secondary School in Hong Kong. Our team was formed in 2019 and we have participated in multifarious international competitions such as Virtual RoboCup Asia Pacific 2020 and RoboCup Worldwide 2021. Last year, our team won second runner-up in the Soccer Lightweight League in Virtual RoboCup Asia Pacific 2020, and this year we are back and aim to get an even better result.
Our aims were to design a completely new frame and remake our system using open source materials, as well as design our own PCBs, algorithms, and omnidirectional camera systems. Most of the components and sensors were self-developed, and the whole R&D process was complete within half a year, which was a huge success for our team.
Our team has continued to develop new algorithms and programs to make our robot more effective. We have also tried to fix some of the problems with I2C communication within our robot. Ultimately, we decided that it was the large resistance of the pull-up resistor on SCL and SDA that were affecting the communication between microcontroller and the sensors. We proceeded to add external resistor in parallel to the original pins, and the original problem has been solved.
This project was started in December 2020. We first planned the prototype of our robot, creating the first draft of the frames and PCBs. We also started developing our own libraries for the sensors. Around February, we finished the first prototype. Here, you can see it chasing the ball, which was a great milestone as it indicated that we were on the right track.
After that, we focused on refining our design and fixing some problems with the prototype. The frame design was simplified and the PCB was redeveloped into a more compact size. More sensors were included to increase the functionality of our robot. This process took around 4 months and we finished the second and final version of our robot in June. We are currently working on internal communications between robots.
So we have designed 5 PCB boards. The most important and the largest board is the main shield. It is used to connect the various components and sensors in the car to the microcontroller embedded in the middle of the board, as well as distributing power to the different components.
The second most important PCB board in the robot is the IR ring. It is responsible for detecting the infrared ball used in competitions. It has 12 pairs of photodiodes and 12 LEDs.
The third PCB board is the grayscale. There are 4 of them placed diagonally, each with 3 pairs of photodiodes and LEDs. They are used to detect the white lines on the field to prevent the robot from going out of bounds.
A shield is designed for the LiDAR and compass sensors, consisting of a small PCB board and several female headers. The sensor shields provide an interface between the sensors and the main shield, as well as having screw holes to allow it to be mounted on the robot.
For the frame of our soccer robot, carbon fiber is chosen as the material as it is light but sturdy and durable, thus able to avoid unnecessary damage to the robots during the game.
We specifically designed the 3D cover for the IR ring to reduce the impacts of environmental light and increase the accuracy of the ball tracking progress. As for the wheels, we installed 4 Omni wheels so that our robot can move in different directions with stable movement.
To provide a 360-degree field of view for the camera, an omnidirectional vision system using a hyperbolic mirror was used. Using the following equations and certain given parameters, an equation for the curve of hyperbola can be obtained.
We then inserted the equation into SolidWorks. We made a 3D model and printed it out, then stuck a mirror sheet on it to turn it into a cone mirror. For more information on how we made our mirror, please refer to our team description paper.
For motors, stereo motors from ZM Robo were chosen. The motors can run up to 1700 resolution per minute and its performance is stable. The motors are connected to the motorboard BTN7971B as it can provide a more precise motor control.
MPU9250 was used as the compass module of the robot. It is a 9-axis microchip module. Raw data is received from the magnetometer and is transferred to the main controller through I2C communication.
Unlike our old designs, LiDAR 3L53LCOX was used to determine range. It emits radiation which can detect objects up to 2 meters away. It communicates with the microcontroller using I2C protocol.
We also added a camera sensor to our robot. OpenMV H7 was chosen. The usage of camera sensors allow our robots to detect the angle and distance of the goals.
We decided to use Mega 2560 Pro as our microcontroller. With the same number of ports, yet 63% smaller in size when compared to the Arduino Mega 2560. It was chosen as the main controller. It was plugged directly onto the main shield.
As we have mentioned before, we also have the custom-made IR ring and grayscale sensors to detect the infrared ball and white boundaries respectively.
Each component has its own unique library to control the input and output of data. I2C is the major communication protocol between compartments. C language was used for the Arduino main controller, while Python was used for the OpenMV camera module. Here is the flowchart of our program. We first check if all data is well received to prevent using users' data. If the robot is facing north and not on any white line, it will start to chase the ball. Otherwise, it will adjust its orientation or position accordingly.
For attacking, our robots are able to capture the ball in a curved movement. The field was defined into 4 quadrants relative to the robot. When the board is at the upper part of the robot, it moves at a slightly larger angle to capture it. The moving angle is linearly proportional to the ball angle. While for defending, the robot moves to the defensive position automatically using the camera sensor when no ball is detected. It moves horizontally along the goal to block incoming balls.
For goal detection, OpenMV camera module was used. The image was filtered using different color filtering algorithms. Our program detects the yellow and blue goals respectively. The angle and the distance of objects were calculated using simple trigonometric functions.
The ball tracking algorithm was divided into 2 parts: data organization and data manipulation. For the first part, the IR ring received IR signal emitted from the IR ball. As our IR ring is highly sensitive and will easily be affected by the surrounding light, the received signal are compared with one another to determine the threshold of ball tracking. Each IR sensor will be calibrated with regards to the data sampled to minimize chances of error.
In order to facilitate the ball tracking process, we developed an algorithm to calculate the absolute position of the ball. We look for the IR sensor with the highest reading and the 2 IR sensors nearby. These 2 values are used to determine which side the ball is closer to, and use the ratio of 2 values to calculate the angle of the ball. With the exact position for the IR ball relative to our robot, we can locate the ball more accurately. We also use a wraparound algorithm to calculate the shortest distance of the ball and use to determine the speed of ball chasing. The chasing speed is linearly proportional to the ball distance and presented in this graph. For instance, if the ball is far away, it will move at a higher speed.
Omni wheels enable the robot to move in multiple directions. We developed an algorithm to calculate the speed of each motor so that it can move in all directions. Each motor was considered as a factor and resolved along the x and y axis. Measured functions like inverse kinematics were used to calculate the relative speed of each motor. But soon we found that the robot moves at different speed at different angles, which affects the ball chasing performance. A function was developed to add sufficient speed to specific motors so that they produce a constant force in all directions.
We developed our own library to calculate the yaw value returned by the gyro. PID controls were included in our motor control algorithm. It is a controller which is used to minimize the error in automation. Proportional integral control is used to set the motor current proportional to the error calculated and change the motor speed when the robot is far from the designated path. The robot will then point at north at all times.
The grayscale sensors are easily affected by environmental light and the color of the right line. At the start of the program, grayscale readings are continuously collected and compared with the previous one. The program then predicts the range of values of the right line and ensures all threshold values are up to date. It will then undergo different calculations, and thus the grayscale value will be adjusted to increase the accuracy of detecting white lines. Both the LiDAR and grayscale will be used to check out of band to reduce noises.
The robot has been successfully tested and developed. Most of the components and sensors were self-developed and performed well during testing. The implementation of open source modules has been able to have similar or even better results than previous builds. It also allows for more flexibility for further development and improvement.
It was a great leap in the R&D department, as this was the first time we had developed a soccer robot using open source materials. The custom-made PCB were able to fulfill their functions and allowed our robots to have the same functionality as before, but using open source materials that could be easily adjusted and changed in the future for upgrades.
With our new software algorithms, our robots can hold the ball relative to its position on the field to maximize the chance of scoring. The choice of grayscale readings has also been adjusted so that it can increase the chance of catching the ball as it is almost out of bounds. The efficiency of other aspects of the attack and defensive movement has also been increased.
If we were asked to promote one part of our robot, we would definitely choose the speed of our robot as a highlight. As we switched from pre-packaged modules to open source modules, the only thing we still used from previous builds was the motors, and it is because it is very fast and yet light in weight. This allows for high speed and accelerations that give us an advantage.
If we were asked to redo our project, further testing on the integration of different sensors and how to use them at the same time will be conducted. We would also like to pressure test our robots to find out any potential problems and allow us to have the time to properly fix them. Moreover, we would like to focus on several aspects to improve our robot. First, the motor ball will be self-developed so as to utilize the space within the robot and reduce the weight. We would also like to develop the camera sensors to detect teammates. Anchor tags or color stickers will be attached to the middle frame of the robots. With development in tracking algorithms, more precise cooperations and different strategies can be provided.
Thank you!